Right, so we were looking at the canonical ensemble, and we derived the connection between thermodynamics and saying that once you calculate the partition function Z, then the free energy, the Helmholtz free energy, is given by minus kBT ln of Z. And once you know this relation, one can calculate all the other thermodynamic quantities. There is one more thing that I want to highlight over here, that one, in the way of calculating the partition function, we had come to this expression that you see over here. Right? What you notice is that kBt square, this exponential factor has minus delta E square to kBt square over C. Now, this necessarily means that C must be a positive quantity. So the specific heat is positive, because otherwise the fluctuations would diverge. Because if specific heat is negative, this becomes a plus and the fluctuations will diverge. So the larger fluctuations are more probable. So thermodynamics also gives you this same conclusion, that the response functions are positive, but it derives it from the stability of the thermodynamic potential. On the other hand, in statistical mechanics, we come to the same conclusion, but from the viewpoint of the fluctuations, right? Now, F is minus kBt ln Z. So let's write this as F bar. The average energy is sum over E 1 by Z e to the power minus E over kBt, where the sum is again over all states. So I note that within the sum, I can manipulate this part by writing del del t of e to the power minus E over kBt, and this is going to give me a 1 by kBt square, which we have seen in the earlier derivation. So if I multiply this with kBt square, then this expression is identical to the one over here. If you are not convinced, you can easily expand this. We can write down this as, if I operate the derivative, it's e to the power minus E over kBt minus E over kB times del del t of 1 over t times kBt square, right? So this gives me sum over e to the power minus E over kBt E over kBt square, times kBt square, and we recover the expression e to the power minus E over kBt. So therefore, the average energy is 1 over Z sum over del del t of e to the power minus E over kBt, right, times kBt square. So I can bring the kBt square outside, and I can write this as 1 over Z del del t of sum over all states e to the power minus E over kBt. Please do not, del del capital T. Do not take the derivative over here, because Z is also a function of t. Then that's a wrong calculation you are doing. So kBt square 1 over Z, this is del Z del t, which is kBt square del del t of ln Z, right? Good, but ln Z is minus F over kBt. So one can replace this over here and take this further, which means I can write down this as kBt square del del t of minus F over kBt. But I have to be careful that there will be two terms, because F is also a function of t. It's a function of t, v and n, and in the denominator there is a 1 by t sitting. Good. The entropy is E bar minus Ts bar. So that the entropy is E bar minus F bar Ts bar. Let's see. Kb T square del T of ln of Z, that is my expression for E bar, minus, this becomes a plus, kbt ln of Z. So this I can write down del T, of T ln Z. I can put a kb over here, and then so now I can take kbt common. If I take kbt common, the first term is del T of ln Z plus ln Z, which is kbt del T of T ln Z. So a furthermore simplification happens if I just put T del T of kbt ln Z, which is minus T del F del T. That is your entropy, right? T times S. Therefore, S is minus del F del T, right? Recall, when we did thermodynamics, we had written F as a function of T, V and N, which is E minus Ts. Well, in thermodynamics it was U minus Ts, so that dF was du minus Tds minus S dt, right? And Tds, du minus Tds, so our Tds was for a hydrostatic system. Let's worry about the hydrostatic system for the time being, was plus Pdv. So the du minus Tds is minus Pdv. So I can replace this as minus SDT minus Pdv, and therefore you immediately see that S is minus del F del T. So we are all going in the right direction. Good. Now let's look at examples of how to handle canonical ensemble. So first thing that we will be worried about is, throughout this we are only going to be worried about non-interacting systems, right? Now when you have a non-interacting system, then the Hamiltonian can be written down in terms of single particle Hamiltonians, right? So that the partition function, the single particle partition function, so well, let's see, the partition function, the total for the whole system is all states e to the power minus hi over kbt, right? Now introduce k1 by kbt as beta, so that beta inverse is therefore kbt, which means this one all states e to the power minus beta hi, sum over hi, sorry, this has to be sum over hi, but the sum now breaks into products. So all states for particle 1, all states for particle 2, so on and so forth. But each of this is what is called a single particle partition function Q. So your total partition function is Q to the power n, right? if the particles are indistinguishable, so for indistinguishable particle, Z is q to the power n over n factorial. Once again, one has to realize that for discrete systems, the free energy is ln of z. Sorry, not only for the discrete system, for all the system, my free energy is k minus kBt ln z. So the z has to be a dimensionless quantity, and we know how to do it for for systems where my state can take continuous values. Good. So we take the example of a two-level system that we had done in the microcanonical ensemble. Here, each particle can be in the energy level 0 and epsilon. So what's first, they're non-interacting. Whether if particle 1 is in in energy level 0, particle 2, particle 3 can also be there, because there is no interaction between 0 and 1 and 2. They are independent of each other in whatever level they are. So my single particle partition function is sum over all states e to the power minus beta hi, and hi is individual particles is epsilon times ni. If you recall, the total energy E was sum over ni times hi, right? So this means that the single particle partition function can be either 1 for corresponding to when the particle is in the ground state with energy 0, or minus beta epsilon. Therefore, the n particle partition function, we will now introduce a subscript n to indicate that this is an n particle partition function. This is q to the power n over n factorial if they're indistinguishable. If they're distinguishable, then this n factorial does not come in, so that we have 1 plus e to the power minus beta epsilon raised to the power n. The Helmholtz free energy is minus kBt ln of Zn, which is minus n kBt ln 1 plus e to the power minus beta epsilon. F is an extensive quantity, which is evident from the right hand side, correct? The energy is going to be kBt square del t of ln z, and ln z is n times 1 plus e to the power minus beta epsilon. So this is del t of n 1 plus e to the power minus beta epsilon times kb t square. Kb t square is n. Del t is going to give me e to the power minus beta epsilon times del t of minus beta epsilon. So this is kb t square n epsilon e to the power minus beta epsilon yeah, this is not right. So we now want to calculate the energy. Now the energy, we did derive the expression, it's kBt square del t of ln of Zn, and ln of Zn is n sorry, this is not the right expression. ln of Zn is n ln 1 plus e to the power minus beta epsilon. So this becomes n kb t square del del t of ln 1 plus e to the power minus beta epsilon, which is n kb t square 1 plus e to the power minus beta epsilon times e to the power minus beta epsilon times del del t of minus beta epsilon. So that this becomes minus n epsilon kb t square e to the power minus beta epsilon 1 plus e to the power minus beta epsilon. Correct? Good. Then it's a derivative of del del beta. Beta is 1 over kb t. Del beta del t is minus 1 over kb t square. So I can replace this quantity, this derivative, by minus 1 over kb t square, so that my average energy E has a very nice and elegant form, which is n epsilon e to the power minus beta epsilon 1 plus e to the power minus beta epsilon. If you recall, this is exactly the form that we got when we treated this problem using the microcanonical approach, right? S, I want to now calculate the entropy. S is minus del F del T, and I just now did the Helmholtz free energy, which is n kb del del T of T ln 1 plus e to the power minus beta epsilon. Note that if I have the energy, I can also calculate the specific heat by using del E del T, right? This I leave it to you as an exercise, but this is also just simple calculus. It's going to be ln 1 plus e to the power minus beta epsilon plus T 1 plus e to the power minus beta epsilon e to the power minus beta epsilon minus epsilon, and then I'll have del beta del T, which is going to be n kb ln of 1 plus e to the power minus beta epsilon plus T e to the power epsilon beta epsilon 1 plus e to the power minus beta epsilon 1 by kb t square. The minus epsilon from here and del beta del T will also carry a 1. This will cancel out, so that this becomes n kb ln 1 plus e to the power minus beta epsilon plus epsilon over kbt e to the power minus beta epsilon 1 plus e to the power minus beta epsilon. And this is the expression for the entropy. One can of course ask that, look, I want S as a function of E and N. That itself is going to be a complicated procedure, because here then you have to from this expression that you see over here, and from this expression you have to eliminate the temperature to write down S as a function of E and N. It is still a doable, and then finally you arrive at the fundamental relation that is very sought after